about QuickSELs, the design and development of QuickSELs, some wafer characterization methods, and finally VCSELs on germanium, which is probably that's pretty much the structure of my thesis. So I'm going to go through the structure of my thesis. Then talk about some other photonics activity in South Wales, brief history of our optoelectronics group, some research projects that we work on and other research groups, and the South Wales Compound Semiconductor Cluster. And then at the end, I'll explain what I'm doing here, the Cardiff-Illinois Strategic Partnership and the funding opportunities available. So for the first part of the talk, producing VCSELs at scale, I want to start off with a description of a VCSEL so we're all on the same page. And I thought I would use an edge-emitting laser for the comparison. So we're talking about vertical cavity surface-emitting lasers, where an edge-emitting laser has feedback into the cavity from the cleaved facets. A VCSEL has feedback into the cavity from epitaxially grown layers. So whereas the amplification is in the plane of the active region for an edge-emitting lasers, it's normal to the plane of the active region for a VCSEL, as is the emission. So we've got cavity lengths on the order of microns as opposed to millimeters, and where we have single longitudinal mode as opposed to multiple longitudinal modes. So some of the advantages of VCSELs: circular beam shape, low power consumption, high efficiencies, and the ability to make two-dimensional arrays. Okay, so here's a timeline of VCSEL commercialization that I had in my thesis. Don't have to go through the whole thing, but the main point is that from the first commercialization in 1996 up until about 2017, volume production of VCSEL was low, or in relatively low volumes, and so production was on small wafers, so 2 or 3 inch wafers, maybe 4 inch sometimes. And then in 2017 there was a big increase in the VCSEL market, and this is because Apple used VCSEL chips in their Face ID and LiDAR scanners. And 2019 is where I started my PhD. So I should make clear that the scale-up of VCSEL production in 2017-ish was driven by IQE in terms of the epitaxy, and IQE was an industry sponsor of my PhD. So it's a UK Research Council funded project with industry involvement. So my research was concerned with the volume production of VCSELs by metal organic vapor phase epitaxy, the assessment of wafer quality, fast, efficient, and reliable testing, understanding non-uniformities and sources of variation, and addressing some of these non-uniformities and improving. So the first results chapter of my thesis was about QuickSELs. So I'll explain why we want to make QuickSELs. There's a textbook definition of a VCSEL product development cycle. The text is intentionally small, so you can't really work it out. But the main point is this happens on the order of months, and some of these steps are iterative. So feedback from testing and characterization back to the epi design, feedback from testing to the epitaxial growth. So these stages as well are occurring on the order of months. So feedback needs to be faster for an efficient product development cycle, and that's where QuickSELs come in. So before talking about a quick VCSEL, I just wanted to talk about a typical VCSEL. So we have a multiple quantum well active region sandwiched between distributed Bragg reflector mirrors, which are doped, high aluminium content layer in the top Bragg mirror, which after selective oxidation provides optical and electrical confinement, usually grown on an N-doped substrate, and then you can make a P-contact metal and N-contact metal on either side of the VCSEL. So QuickSELs then, as I later coined, are a single etch, single selective oxidation, P-contact, N-contact, very simple process. So we just use a weird shaped meser with some wires which expose the high aluminium content layer in the DBR. Then after selective oxidation, we have a region that's electrically isolated and a region that forms the aperture, so where you get the light emission. So there's no passivation, no planarization steps, and the processing time in total is about 24 hours. So just a quick overview of some of the performance you get out of the QuickSELs. This is all on 940 nanometer epi structures, sub-milliamp threshold currents, tens of milliwatts output power, slope efficiencies above 1 watts per amp, power efficiency 40%, single mode and multi-mode spectra depending on the oxide aperture, resistance that's representative of typical standard VCSEL, far field divergence angles that are also representative. And these results are repeatable, so you can measure the same device many times, get the same answer, and there's negligible degradation over time. So if you went to measure the same device in a year's time or 2 years' time, which I have done, you get the same answer as well.
Hey Jack, why 940?
So 940 is the platform that's been commercialized, so that's what's in the consumer applications. So all the work we did basically was on that already commercialized epi structure. But we do, this is just for the qualification of the device structure. We do development on different epi structures as well, but this just happened to be where we qualified the device structure. So some things it can't do though, it's not good for a representative lifetime or reliability test, and the modulation response as well, it's not representative. So there's some variations, so 940, 3D sensing LiDAR applications, that's your standard QuickSEL, or our standard QuickSEL. And then sometimes developing EPIs for atomic clock magnetometer applications. So they can be grown with an anti-phase cap, so it requires an extra etch step, quarter wavelength etch step, which I'll talk about a bit in the next slide. And then some epi structures designed for datacom applications, so they can be grown on a semi-insulating substrate. So both the contacts need to be on the top side then. So that requires another etch, another deposition on top, which obviously affects the processing time, but still 30 hours for the most complicated QuickSEL. And then in comparison to a full high performance datacom VCSEL, it's a huge reduction. So I just want to explain a bit more what I meant about in-phase, anti-phase. So looking at the top layers of the top DVR, an in-phase structure would be where all the layer thicknesses are quarter wavelength, quarter material wavelength. Anti-phase structure, then the final layer is grown as a half wavelength thickness. So then what you do is etch a quarter wavelength thickness, and I have regions where you have anti-phase reflections, in-phase reflections. So this is used for mode control. In terms of the QuickSEL though, we're just making everything in phase, then performing the same test and characterization and analysis. So we qualified that as well. So we've got your standard, these are performed on a same wafer devices in close proximity, as grown versus quarter wavelength etch. So the black curve is the as grown, and then after a quarter wavelength etch, you see is a huge reduction in the threshold current, which is even more obvious there when we look at the function of oxide aperture for large amount of devices. Then also qualified the top side end contact need for growth on or structures that are grown on semi-insulating substrates, looking at the effect on the resistance of the device. It's pretty much equivalent, and then again, more obvious when you look as a function of device size, and for a larger amount of devices, no effect on the resistance by depositing on the backside or the top. Okay, so that was an overview of QuickSELs. Second part then, techniques for the assessment of VCSEL wafer quality and uniformity. So typically we're processing wafers on 4-inch diameter for datacom and atomic sensing applications, and 6-inch for 3D sensing LiDAR 940. So yeah, 2 wafers there, both covered in QuickSELs. And actually I created my own light box for that photo, which I'm kind of proud of. So there's some inline characterization that's done by the grower as part of the foundry process. So reflectance and photoluminescence mapping. So I've got a schematic there for a nanometrics reflectance PL wafer mapping tool. So there's a broadband source for the reflectance measurement, 532 nanometer laser for the PL measurement, and then the spectra are measured at thousands of locations on on the wafer. And yeah, as I said, this is performed by the grower. So a little bit more about reflectance. This is performed on every wafer, on the as-grown structure throughout full growth campaign. Extract important characteristics from each spectrum. The cavity mode wavelength has the dip in the stop band. Get the stop band width and center. See how the center aligns with cavity mode wavelength. The stop band height as well, which is uncalibrated but can be used to assess variations in the mirror reflectivity across individual wafers. But yeah, the most important is the cavity mode wavelength, which determines the emission wavelength of the VCSEL, and this is determined itself by the composition and thickness of the inner cavity layers. So how the cavity mode wavelength varies across a 6-inch wafer. So you can see it's radial with a longer wavelength at the center. So the wavelength itself is the product of the refractive index and the thickness of the cavity. So the shift of short wavelength to the edge is representative of a reduced layer thickness and potentially composition as well. That just says and. Okay, so photoluminescence as well. So these aren't performed on as-grown structures because the DVR influences the spectra you get. So these are performed on calibration wafers at the beginning of growth campaigns. So they're grown without top DVR, sometimes just grown on substrates, just the active region. So PL wavelength is something that's specified in the design of the structure, the epi structure that is, and is representative of the quantifier layers. So the PL wavelength is always designed to be shorter than the cavity mode wavelength. This is to account for self-heating effect, band gap renormalization, quantum confined Stark effects in the actual device, and also to allow room for a detuning of the gain peak and cavity mode wavelengths. But the relation to the gain peak isn't trivial, so it requires the processing of VCSEL devices anyway to assess that. Also extracted from the PL spectrum then the intensity, line width, and the integrated signal, which can indicate if you have a high density of defects in certain areas on wafer.
Is 16 nanometer detuning a typical offset between your PL and cavity resonance?
Yeah, so I'll show now some comparisons of PL, cavity mode, and then the actual device, all for the same wafers, or not the PL from the exact same wafer, but from the beginning of the campaign, yeah. So I think so, but it depends on the wavelength, target wavelength of the VCSEL, the actual device. But it would appear so. I didn't do the designs, but...
Okay, but and the other question I was wondering is, your cavity resonance is designed at 940, so that means when the VCSELs are operated, they're going to be a little bit longer wavelength. Is that okay for whatever the application is?
I think for this, yes. Like, so a 10 nanometer, there's a 10 nanometer tolerance on the actual application. So if I show the cavity mode actually, the cavity mode, like that is a 99% in spec wafer. And clearly there's a 10 nanometer variation, but still in spec in terms of the epi related to the specification for the product.
Okay. But you're better than 10 nanometers. I see that's like 5 nanometers from center to edge.
Center to edge, yeah. Well, actually,
Well, I mean,
really shifts.
your edge is falling off a cliff, but if
Yeah,
you stay
yeah,
away
it
from that
falls
cliff,
off.
it's pretty. much
It's
more-
pretty good.
That's actually amazing. That kind of uniformity. Just.
I mean, yeah, I should stress that this is coming from IQE, and that is their business, is to produce VCSELs that do the same thing every single, at least epi that does the same thing every single time with a very high yield.
Right, to put a perspective on this, if you look at that data, that central region there that's red, that is all within 1 nanometer, that's about the size of the wafers we were working with, even 20 years ago. And they weren't and they were far less uniform. So these are amazing.
Yeah, there's a lot of things I think that they tweak to make sure that it is this uniform. Although if we're looking at smaller wafers and more demanding applications like the atomic sensing, they require 894.6 nanometers, plus or minus 0.1 or something like this. The yield is obviously very much lower than when you think about it. Okay, so yeah, spoke about PL. This is how PL wavelength and PL peak wavelength varies on the wafer. It's still radial, but and also shorter wavelengths at the edge. But you probably notice a lot the center to edge variation is a lot less than the fabric barrier or the cavity mode wavelength. Sorry. And this is telling us about the quantum well layers, so the thickness of the quantum well, the composition of the quantum wells, and then a comparison, taking a line profile across two of those heat maps. Cavity mode 5 to 10 nanometers usually. The PL is more like 1 or 2 nanometers. And this is just because the cavity mode wavelength is much more sensitive to the layer thickness variations, and PL is, or the quantum well transition energies are to thickness variations. So, talked about QuickSELs previously. So QuickSELs are also part of the wafer assessment techniques. So, process wafer with a lot of QuickSELs and then characterize them all over the wafer, and this is our setup for doing that. So it's a semi-automated wafer mapper, CW and pulsed current sources. Then that's an integrating sphere that sits above the VCSEL, collects all the light. And there's a calibrated power meter then for true optical power measurements. There's a fiber tap from the integrating sphere that goes to an array of spectrometers. So this covers from like 200 nanometers to 1700 nanometers. So we also measure some other devices on this system as well. The chuck is temperature controlled to 200 degrees and also not pictured, but we can swap out the integrating sphere for a beam profiler that measures the far field divergence angle and the intensity profile, and we can swap out the integrating sphere for motor controlled polarizer, so we can do polarization dependent measurements on wafer as well.
Can you capture all that simultaneously?
No, we can't do far field and polarization. That has to be separate. We can do PIV wavelength all in the same automated test run.
And polarization?
No.
Okay, that might be.
You have these separate test runs.
Okay.
Yeah. We can't do polarization resolve spectrum on wafer.
And is that an environmental chamber, or is that in air?
Yeah, it is air. It is air. But I don't know if you can see that logo there. Shield environment.
Okay.
But yeah, it's designed to make sure when you actually want 200 degrees, it is giving you 200 degrees. It's easier lower temperature. Okay, so I'm just going to show then how some VCSEL performance varies as a function of position on the wafer. Emission wavelength is quite straightforward, representative of the cavity mode wavelength. We've got extracted peak wavelengths there, plotted against the cavity mode wavelength and the reflectance mapping, overlay very nicely. Something else that needs to be considered when assessing the variation of device performance is the oxidation rate variation, and that's highly dependent on your method of oxidation. So on the left is the oxidation extent, so the final oxidation extent variation for a 6-inch wafer that was oxidized in a conduction-based furnace. So the temperature control relies on thermal contact with the heated chuck. So gas wafers at 6-inch bow, so you get this lower temperature in the center, higher temperature at the edge. That's why you have a longer oxidation extent at the edge, shorter in the center. But then you can use a method of oxidation that relies on just the ambient temperature, so a convection-based furnace, and those will give you a much more uniform temperature distribution across the wafer, and therefore much more uniform oxidation length variation. And I should just say that the oxidation extent variation has a big impact on the device performance, threshold current, oxide aperture, series resistance. Did I say oxide aperture or output power? I meant output power. Okay, so I'm not going to go through every single parameter of the map here, but I'm going to show the threshold current density variation. So to get rid of that oxidation effect from the device, we can look at the threshold current density of large aperture devices where any variations in the oxide aperture are less important. And there's still some variation in the threshold current density that remains. So yeah, higher in the center, lower towards the edge, right? If we assess the temperature dependence of the threshold current density at various locations on the wafer, get plots like this. So the black triangles for the center, white triangles for the edge. So it's clear that there's a difference in the temperature that corresponds to the minimum of the threshold current density versus temperature plot. Okay, and so what's physically worked there is an offset between the gain peak wavelength and the cavity mode wavelength, and that varies as a function of position on the wafer. So at the center, at room temperature, we have the case where the cavity mode wavelength is longer than the gain peak. That's as it's designed, so that when you operate at higher temperatures and higher biases, those two wavelengths will align. But at the edge, that's happening at room temperature at the biases that we're working with. So there's a spatial variation in the detuning of the gain peak and cavity mode wavelength that shifts the minima on these two plots. And actually, if you were to look at the variation or the non-uniformity at a higher temperature, that actually improves as a function of temperature. So the overall picture for wave characterization then, just want to really draw attention to some of the things I haven't mentioned that go on. So there's inline material characterization. I talked about reflectance and PL, but there's also X-ray diffraction, electrochemical capacitance voltage to assess the doping concentrations, surface scan for defects. Then we got the fabrication of devices across a wafer. Talked about how the oxidation extent might vary. There's also etch depth variations that are measured, profilometry, so of the metal contacts. Then the on-wafer test of VCSELs showed about emission wavelength threshold, but we can also look at optical power, differential efficiency, series resistances, and their temperature dependencies as well. And then finally, some other things that we include on the on-wafer testing, some different test structures, so circular transfer length method structures for assessing contact resistances, sheet resistance, and we also have some structures to measure the oxidation extent from electrical measurements. So essentially VCSEL mesers, but they don't laze, covered with metal, that you can measure the resistance change as a function of device size, and then fit to the data to see what the oxidation extent is. So then the final part of my thesis was on VCSELs grown on germanium substrates. So firstly, I guess the question is, why not just gallium arsenide like it usually is? So the issue is with the bow, as the wafer diameter is increased for VCSELs grown on gallium arsenide. So there's a bit of strain from the very slight lattice mismatch between gallium arsenide and aluminium arsenide or high aluminium content algas. But we have a lot of layers in the VCSEL, and as you increase the diameter of the substrate, that strain results in a bowing of the wafer. And that gets worse as you increase the wafer diameter. So why germanium? Germanium actually has a better lattice match with aluminium arsenide or high aluminium algas. And there's a few other things about germanium. It's high fracture toughness, zero defect density, and something that I'll go into more detail to assess the effect of the higher thermal conductivity of germanium as well. So just to show you some data that shows what happens between gallium arsenide and germanium substrate wafers for the wafer bow, measuring the surface height variation as a function of position for a 6-inch germanium gallium arsenide wafer. So you can see it's pretty flat for germanium. That's just representative of the surface height variations of the substrate. And then you can see a 130 micron center to edge height variation for the gallium arsenide that comes from the bow. So essentially, I would say probably the main reason that anyone was talking about growing on germanium was the fact that the wafer doesn't bow on germanium, and this is beneficial if you want to go for 200 millimeters or 8 inch instead of 6 inch. So
What size is this substrate?
6 inch.
6 inch?
Yeah.
So that's a comparison of germanium to gallium arsenide directly.
Yeah. Yeah. But so one of my colleagues was presenting about 8 inch VCSELs on GaAs and germanium at ISLC. So that's also happening, yeah. So past work, which I just ruined what I was about to say now. Past work then, so there's the first demonstration of VCSELs on germanium from IQE. And then we've done some work together with IQE, so assessing the impact of the wafer bow on uniformity, the potential for growth on thinner substrates. So I mean that's just a cost benefit for germanium. And then yeah, the 200 millimeter development, which is to be presented next month at ISLC. So there is some other people working on VCSELs on germanium as well. So University of British Columbia, National Taiwan University, been working together, and their reports have been more focused on the engineering of the transition between germanium and gallium arsenide, crystal quality, defect density, things like that. But they have produced now some full VCSEL structures on germanium, and also some decent data from those VCSELs grown on germanium. And then one of the things they said actually in this paper here was that they were intending to demonstrate the superior heat dissipation properties of germanium and how that will benefit device performance, which was something I tried to do in my thesis, but the errors were such that they looked exactly the same. So I thought I'd revisit that, and then the next bit of this talk is pretty much just the things I'm going to talk about at ISLC next month. So thanks for letting me have a quick run through. Typical device structures, again, the only difference nominally is the germanium to gallium arsenide transition. We're going to look at the power current, voltage, and optical spectra for both GaAs and germanium devices, extract threshold currents, rollover currents as a peak power, and turn-off currents. Look at this as a function of oxide aperture, same for series resistance, and then the emission spectra, look at that as a function of current and temperature, and the IB as a function of temperature as well. Put all that together, compare the room temperature performance essentially, and also the thermal performance. So extracting the threshold currents, threshold current densities for devices from the center of a 6-inch wafer. The threshold currents overlap very nicely, the threshold current densities are about the same. Looking then at the rollover and turn-off points, these also overlap very nicely. So it's looking like things are the same between them. And I should say as well, there's a plus or minus 0.5 micron oxidation extent uncertainty, there's an upper limit of the oxidation extent uncertainty. So when you account for that as well, they definitely overlap. So I wanted to verify as well that the internal mechanisms or what's going on inside the device is the same in the epi, so isolating the substrate effect. So I wanted to probe the internal temperature, compare that for GaAs and germanium devices, but then there's a few methods you can use to gauge the internal temperature. You can look at the wavelength shift as a function of current, but then over large current ranges it's quite hard to track individual modes. You get a scatter, you get potentially a sizable uncertainty, so you have a big uncertainty in your calculated temperatures then. You can look at the wavelength shift as a function of dissipated power, so essentially calculate the thermal resistance, multiply that by your dissipated power. But it relies on some assumptions, and also the thermal resistance is something I want to compare between them, so I wanted something separate. So actually you can look at the turn-off current, so the current at which the PI rolls back down to zero, or the power rolls back down to zero. And there's an important fact about it, that it's independent of heatsink temperatures, so that temperature is the same as you vary the heatsink temperature. So measure lots of PIVs as a function of heatsink temperature, There you go. So from 25 to 150 degrees Celsius here, and then extracting the threshold current, rollover current, turn-off current at each of the temperature intervals. Then these converge at a certain temperature, certain heat sink temperature, and that's the point, the temperature corresponding to the maximum CW heat sink temperature. But then, if we extrapolate the red curve, the turn-off current down to white is 0, then this is representing the average cavity temperature at turn-off. So that's what I'm going to compare between the devices. But I looked at it as well as a function of aperture size, expecting it to be constant, but actually finding that you have a lot flatter variation with temperature, say turn-off and rollover, for a small aperture device, which pushes out that turn-off temperature compared to a large device there, which drops off really rapidly. So then when I plot it all out, we get clearly a decrease as a function of oxide aperture, and then just revisiting the story of gas versus germanium. Even if you account for the variation, the 0.5 micron uncertainty in the oxide aperture, the plots probably won't really overlap. So there could be some difference in the internal mechanisms. But regardless, measuring the thermal resistance then and comparing that for gas and germanium. So the thermal resistance can be expressed as the ratio of the temperature rise in the device to the total dissipated power. But the temperature rise is not directly measurable, but you can measure the wavelength shift with dissipated power and the wavelength shift with temperature to get the thermal resistance. So the dissipated power here is the electrical power minus the optical power, and this does assume that all the dissipated power is generated in the active region. So example of the data sets, so we've got peak wavelength versus dissipated power as a function of temperature. Then we can get the wavelength shift with dissipated power from slope. Extrapolate to 0 dissipated power and see that as a function of temperature to get the wavelength shift with temperature. Okay, so we want to do some fits to that data as well to extract conductivities. So this is the thermal model for that. This is our device on a heat sink. So we've got the substrate, the DVRs, the PDVR is etched, the NDVR is not etched. So the NDVR is actually grouped with the substrate in this model. Heat generated at the active region with some heat flux to the heat sink. And then the diameter of the substrate is ds, has a thickness d, which also includes the NDVR. And then meter diameter dn, oxide aperture diameter dox. We can use this analytic expression for the thermal resistance to fit to the data. So that's the full expression, but in our case we're measuring it on wafer, so the substrate diameter is huge compared to the substrate thickness. So the first term on the right hand side disappears, and as well the substrate diameter is a lot larger than the oxide aperture diameter, so this bracket term goes to 1. So then we're just left with this expression, which we can fit to the data to extract the thermal conductivity. So this is what it looks like when we do that. We got in this table here thermal conductivity values from that fit for gas and germanium. That includes the bulk values as well. So bulk values 5.55 for gas, 0.58 for germanium, watts per centimeter degree Celsius. So that difference, or the ratio, the gas to germanium ratio is about 0.95. But then our extracted values, the ratio is about 0.88. So begs the question, why is the difference more than the difference in the bulk values if the only thing we're changing between the structures is the substrate? So we looked at the electrical resistance, found that it's quite consistently higher for germanium VCSELs. So it's about a 20 ohm offset quite consistently, and the location of that extra resistance, where that's coming from, is important. So if from the P contact, or the PDVR, the NDVR, they're close to the active region, it could probably be included with the dissipated power from the thermal resistance calculations. But if originating from the substrate or the end contact, because they're far away from the active region, we need to correct the dissipated power from the thermal resistance calculations. So we looked at the contact resistance from the P contact from TLM measurements, both 7 times 10 to the minus 7 ohm centimeter squared. Sheet resistance, comparable as well. So the extra resistance is not coming from the P contact, is likely not coming from the DVRs as well. So then, if that dissipated power is coming from the end contact, it needs to be corrected from the original dissipated power from the thermal resistances. So we included this RC term here. That's 20 ohms, that's the offset between the measured resistances. And then clearly the plots over a lot closer than they were previously. And then that gas to germanium ratio is now 0.97 as opposed to 0.95. So actually a lot closer to the bulk value. So that basically summarizes the thermal performance comparison. It's a lot less than I originally thought, and that's because of the substrate or end contact contribution to the series resistance and having to correct that from the dissipated power values. More closely matching the bulk values now. So really I think it's quite difficult to see any difference in the device performance originating from this difference in thermal performance, if any. You need to know so many things about your device are exactly the same in order to probably be able to resolve any benefit. So I think really, yeah, they're about the same, gas and germanium, in this respect. Okay, so that was basically all the stuff from my thesis and the ISLT talk was coming out. So I was going to also talk about other research in photonics happening in Cardiff. I'll try to be quick actually. So just a quick history. The group was founded in 1990 by Professor Peter Blood, which I think who you know, Kent. So he was formerly of Philips Research Labs, resident visitor at Bell Labs actually, and the research focus for the group was the physics of absorption, gain and recombination in quantum confined edge emitting lasers, quantum wells and dots also featuring quite a lot. I should also mention, because I'd be ostracized otherwise, that there's a development of a novel gain and absorption measurement that came out of the group, the segmented contact technique, which is detailed in Peter Blood's textbook, of which we all have a copy, don't we, James?
And
so
it's used in 532, which is the grad laser course.
Ah, nice, that's cool. Okay, so what's actually going on in South Wales? So we've got this South Wales compound semiconductor cluster, has become named. It's the United Kingdom, this is where we are. And this is a map of South Wales and some of the compound semiconductor players that live there. So it's government, funding, industry, universities. So Swansea and Cardiff universities. And then IQE, I've spoken about already, they sell EPI. A few companies that so Microlink sell photovoltaics, Microchip do packaging, KLA, they focus on etch tool development in South Wales. And then we have also CSE, which is quite important for us anyway, which was a joint venture between Cardiff and IQE, whereas IQE focused on volume EPI production. CSE were focusing on R&D, so it's like small batch EPI, testing out new ideas with the idea of eventually they can be scaled up next door in IQE. So if we have research projects and we're growing structures, developing structures, it's through CSE.
What did CSC stand for?
Compound Semiconductor Center. It's not a great name, I think, really,
Yeah.
but okay, so this is, for reference, how big is the cluster? it's a 1 hour drive from the two furthest points really. Swansea to Newport is a 1 hour drive, so we're all quite close. Right, so this is where we live. We've lived here not very long. Translational Research Hub, so it's us, compound semiconductor people, and then there's also some chemists, but it's all about taking research and translating it to industry. So also housed here is the Institute for Compound Semiconductors. I mean, they have the same MO, but it's all about fab. So it's a 1,500 meter square clean room that's, you know, companies can come and pay for that use, or we can pay for that use through research grants, but essentially it's making manufacturable processes for compound semi. So some of the actual photonics research activities that we work on, not me personally, but the group in general. So we've got Pete Smoten and Sam Schutz who lead the group. So there's a lot of quantum dots, lasers on silicon work, integration. So we've got here high reflectivity laser facet for PICs. These are just scattered, there's no particular order to these. So this is passive mode locking, 730 nanometers, just to give a flavour. The design for a tunable, 100 nanometer tunable laser for PICs, and that's a SEM image of the characterisation. This is including, like for a VCSEL, aluminium oxide and passives in integrated circuits to improve the confinement. Some GaN LED development. Okay, 8-inch VCSEL development, which I said is going to be presented at ISLC. Is an interesting laser ring resonator coupled cavity. Some of that example of the gain absorption technique, segmented contact technique applied to 1.5 micron quantum dash laser structures. What we got here, we got a waveguide outcoupling grating and a third order DFB grating as well there. And also something that we really like doing is processing a dragon on your couple VCSEL arrays. That's a courtesy of James over there. And I would just say a few things about some of the research projects we work on. There's a lot of focus on scalable processes, optical communications and sensing. Like I said, the quantum dots on silicon is a joint venture with Southampton, Cambridge, University College London. And then, yeah, I thought I should include this. We have a centre for doctoral training. I don't think we have, I'm not sure you may do some stuff like that in the US. So students come in and do an MSc, and then it's integrated with a PhD with a sponsor from industry for every different project. So I thought that's worth including. Maybe this is not of interest, but the other research groups that we live in the same building as, some colloidal quantum dot synthesis work, single photon sources for quantum applications. This is a non-exhaustive list, by the way. Quantum dot growth, nanowire production, cubic GaN stuff. So Dave Wallace spun out a company recently which uses his cubic GaN epitaxy techniques. So then finally, I was going to explain what I'm doing here and the Cardiff-Illinois Strategic Partnership Agreement. So that was signed between our two universities last year. In the picture there, on the right is Pro Vice Chancellor from Cardiff, and then on the left is, does anyone recognise that guy?
Yep.
Yeah, President of Illinois. He's actually from Cardiff, I learned.
He is?
Yeah, he spoke at my graduation ceremony.
Oh, we
And that's where I realised that, so that's quite cool. So this is why I'm here now, is the Joint Research Seed Grants. It's a 5-year call, annual call for proposals, and the second call is open now. Seed grant funding, actually we were successful on travel grant funding, hence my being here today. And so the particulars of why I'm here today is for a proposed project with Ken Chiquette's group, combining some of his early work on photonic crystal VCSELs with wide wavelength range single mode properties with some novel epi development for targeting different applications. So yeah, I'm hopeful about that project as well. I'm really happy to be here. Thank you very much for listening to me. And this is our university mascot in Champagne this morning watching the sunrise. So this is my gift to you. Thank you everyone. Cheers.